Okay guys, so now can you hear and see me? Okay guys, so now can you hear? Yeah? Okay. Awesome. So let's get started. Today's question, it was a good question of mediocre category because it is not one of those conventional questions. It's a new question, I would say. Not very hard, not very easy. A good medium question which forces you to use your brain and build a solution right from scratch. So a good interview question. Have you read it? How many of you read the question and made an attempt to solve it? Can you say yes if you did? Rachit is saying it felt to him as if it was slightly above medium. Okay, that's why I said good medium question. Maybe something in between medium or hard. Yeah. Okay, Aniket and Faizan, they gave some time to read and understand the question. Okay. Okay, so what we all can do is we all can together read it once again. Maybe when you read it once more, it gives you a different dimension. It helps you pick the right things. See, first thing I would tell you guys is whenever you are reading a question, you have to take note of some important keywords. I mean, you have to use your brain that, hey, why so and so keyword has been used in the question. So like when I read it, it says that given an array of unique integers. Okay, why unique? Why they have been kept unique? There must have been some reason for it. I mean, no problem statement would just say unique for no reason, right? So this is something which should be there inside your head. So we'll just make a note of it, that integers are unique, and now we have to think why, probably why. Okay, the name of the array is ARR, where each integer is strictly greater than 1. Now this is another thing that we should take a note of. So here it says that inside your array everything will be greater than 1. It will be positive and greater than 1. But why greater than 1? There must be some reason behind that, which we'll probably decipher in some time. Okay. Now the next thing, we make a binary tree using these integers. Okay, so all of you I believe know what is a binary tree. A binary tree is a collection of nodes and edges. It is an acyclic graph, you can say, connected, and a node can have at max 2 children, right? So that is the property of binary tree. So for example, I mean, let's say there is a node 8, and let's say it has a left child, and then it also has a right child, and let's say the left child of 8 is 10 and the right child is 9. Now similarly, 10 can also have at max 2 children. 9 can also have at max 2 children. When I say at max, the important thing to keep in mind is that there can be one child also and no child also. For example, let's say the node 10 only has a right child, and let's say that right child happens to be 18. So now if you look at this tree that I have drawn for you, in this tree 9 and 18 are my leaf nodes. So all of you know leaf nodes. Leaf nodes are those which do not have any children. 8 and 10, they are non-leaf nodes, right? Okay, so let's read this paragraph again. So we want to make a binary tree using these integers which are given in the array. Each number may be used for any number of times. Now this is a very, very important thing to keep in mind. So what it means is that let's say you are looking at a number 2. Okay, now you can use this 2 for multiple nodes. So I can put a 2 here also, and I can put a 2 here also if I want, and I can put a 2 here also. So basically you can use an element as many times as you want. It's totally up to you. Okay. Now each non-leaf node's value should be equal to the product of the values of its children. Product of the values of its children. So it simply means, let's forget about this for now. Let's say there is a node here, and let's say its left child happens to be 10 and right child happens to be 5. That means the value of this should be 10 into 5, that is 50. This is the requirement. So each non-leaf node should be equal to the product of value of its left child and right child, as simple as that. Of course, leaf node will not have any children, so this rule is for non-leaf node only. Okay. Now what we have to do is we have to return the number of binary trees we can make. So how many binary trees we can end up making if we have to take care of this consideration. Now it also says that answer might be too large, so large that it might not fit inside an integer or long integer. So you just have to return the answer modulo this. Modulo of anything with this will result in a value which is smaller than this, and at min 0, right? So that is the question overall. So this is what we are supposed to do. So when you look at this array as an example, it has 2 elements, 2 and 4. Now see, the question never told you that you have to use all the elements. So certain people, when they read the question, they feel that, we have to use all the elements. Does the question ever say that you have to use all the array elements while making your binary tree? Yes or no? No, it never says. It simply says that an element may be used multiple times. That's all that it says, right? So it simply means that maybe what I can do is I can just pick this value 2 and I can create a tree which has a single node, that is 2. That's it. So this is one possibility that I can have. Similarly, I can just pick this 4 and create a tree which just has a node 4, right? So these are 2 very simple binary trees that I can make. One more binary tree that I can probably make is I can take this 4, I can put this as node, and if I do not want this to be a leaf node, then it must have a left child and right child. Now it is important that the product of left and right child should be equal to 4. So what can I do? Can I pick this 2 and assign it as the left child? As the left child of this 4? The answer is yes, I can do that. But hey, can I pick this 2 again and assign it as the right child also? The answer is yes, again, because each number may be used multiple times. So I can pick this 2 and put it up here also. So overall, this, and that. These are the 3 different trees that are possible. So the answer is 3. Is everyone clear with the problem statement and this particular example now? Feeling comfortable with what the question is saying? Yeah? Okay. So if you understand that, now you can have a look at this example and try making sense of it. That the answer for this is 7. See, if the size of array is n, can I say that my answer will definitely be greater than or equal to n? Can I say that? Let's say your array has 4 elements. My answer will always be greater than or equal to 4. Why? Because, to be minimalist, I can take each element and just have that element as the only element in a binary tree. So you can take this 2, put it here. This is a binary tree with just one node, which is the root node as well as leaf node. Same for 4. You can have 4. Same for 5. Same for 10. So I can definitely have n different binary trees with only one node inside them, and those one nodes could be this 2 or 4 or 5 or 10. Now here, as you listen to me here, one thing must click in your head. Because there are no duplicates in the array, so there won't be any duplication in these sort of binary trees. Are you getting my point? Yes or no? Right? Okay. So that is one thing to note. Now let's move on. So these were some trivial ones, obvious ones, right? Now, question also said that every element is going to be greater than 1. We will decipher why this was there, if at all. Now we have to think little carefully. Now we have to think about non-obvious trees. By that I mean the trees in which I am going to have more than one node, right? More than one node for sure. So for that, can you guys look at my Google Doc? Is it visible to all? You can just let me know. Yeah, everyone can. Okay, great. Let's say you had been given an array. This array had so many elements, and let's say one of the elements was 20. After 20 also there were so many elements. Now think of it in this manner. So I am going to write few things which already were stated. Unique plus all elements greater than 1. This requirement was already stated, right? If I ask you one question, one simple question, that how many trees will be there whose root will be 20? How many trees will be there whose root will be 20? Then how will your brain start to process this? How will your brain start to process this question? Your brain should start to process this question after referring to this rule, which says that each non-leaf node's value should be equal to the product of left child and right child. Correct? So basically, you will start to think that the left child, if the left child is x and the right child is y, then x into y should definitely be equal to 20, isn't it? Tell me, yes or no? Right? This is definitely that you will come across. Now, does that mean figuring out the factors of 20? Factors of 20, yes or no? The answer is yes. It definitely means figuring out the factors of 20. What are the factors of 20? Can you guys type it quickly in the chat box? 1, 2, 4, 5, 10, and 20. These are the only factors of 20, isn't it? Right? So I can say that, hey, if x is 1, y has to be 20. If x is 2, y has to be 10. If x is 4, y has to be 5. So what I'll have to know is that how many binary trees are possible whose root is 1, or whose root is 20, or whose root is 2, or whose root is 10, and so on and on and on. This is something that I would want to know. Now tell me one very simple thing. The question clearly says that all the values are greater than 1. So is it worth considering 1 as a potential factor and as a potential tree, be it left tree or right tree? Is it worth considering 1? The answer is no. It is not at all worth considering 1. So what I'll do is I'll get rid of this 1. Right? Now, if you don't consider this 1, is it worth considering 20? The answer is no. Correct? Because there will be no other value 20. Everything that is present is unique. Correct? So these conditions were there, that all the values will be greater than 1, and at the same time everything will be unique. Because if you had any 1 inside it, if you had even a single 1 inside it, then you would have to figure out that how many trees with a product of 20 would be there. So now does this requirement make sense, that why this was a part of the question? Yeah. Now when we understand why this was a part of question, so now it means that our candidates for x and y can either be 2, 10, where x is 2 and y is 10, or it could be 4, 5, where x is 4 and y is 5. Now what is it that you would want? So let's say if you are talking about this particular case, you'd want to know that how many binary trees are possible whose product is 4. How many binary trees are possible whose root is 4? So let's say there were some values in here, and those values were, let's say you had a 2, and then after 2 somewhere you had a 4, let's say this was the situation. Can you tell me that if this was your array, these are the elements that you know for now, then how many binary trees would be there whose root would be 4? So the first possibility could be that you just have a binary tree with only one node, that is 4. And the second possibility is that you have 4 and then you have a left child of the 4 and also a right child of the 4, and both of them can be this 2 because this 2 can be used multiple times. Correct? So what does it mean? It means that there are 2 possible binary trees whose root is 4. There are 2 possible binary trees whose root is 4. Similarly, if I ask you, let's say you had a value 5 over here, right? And if I ask you that, hey, how many binary trees will be possible whose root is 5? What will be your answer? What will be your answer? The answer will be only 1. Correct? Why? Because you can just have this 5 and have this 5 as the only node in the tree. So now what does it mean? It means that your x, which was supposed to have a root as 4, there are 2 possibilities for it, this or that. Similarly, your y has 1 possibility for it. So what will be the total number of possibility? What does the basic rule of product of mathematics says? If number of possibilities for this is m and number of possibilities for this is n, the total number of possibility will be Cartesian product, which is m into n, right? So 2 into 1, which is 2, right? So I can say that, see, now you can note it quite easily that you can either have this 4 over here and this 5 over here, right? So this is one valid binary tree whose root is 20. Or you could have had this thing, this other tree as the left child and that 5 as the right child. So that would have given you something like this. If you want me to draw, could be something like this, right? So there are 2 possibilities. But one more thing. This 5 could have been your left child also, and that 4 could have been your right child also. So if I just switch the roles, if I just change the roles, this 5 could have been here and this 4 could have been here. Now in this case also 2 possibilities, that for 5 you just have this tree, but for 4 you could have had this first one also and you could have had this second one also. So I can say that the number of possibilities that are there for 4 multiplied by number of possibilities that are there for 5 multiplied by 2, this is going to be the total number of possible binary trees whose root is 20 and left child is 5, right child is 4, or 4, 5. Correct? So this is going to be the total number of binary trees that belong to this category. Similarly, you can evaluate in this section also, that how many possibilities are going to be in this section. Are you getting this point? How many of you are able to follow it so far? Like say for example you pick this category, if you pick this case, and if I ask you to take a look at this, can you tell me how many possibilities will be there for 2? I mean, how many binary trees will be there whose root will be true? Whose root will be 2, not true, 2. Only 1, right? Only 1. And what is that? You just have 2. Okay. Similarly, if I ask you that how many binary trees are possible whose root will be 10, what would you say? For that you would question me that what are the values. Let's say you have 10 as a value here. So one possibility is that you just have a 10 and the job is done. Second possibility is that you have a 10 here and then you have 2 as the left child of 10, correct, and 5 as the right child of 10. And the next possibility could be the reverse of it. where you have what? Where you have 5 as the left child and 2 as the right child, correct? So total number of possibilities in this category would be 1 multiplied by 3 multiplied by 2, because if you have 2 as the left child and 10 as the right child, you can also have vice versa, which is 10 as the left child and 2 as the right child, correct? Are you able to follow this point? How many of you guys are able to follow this point now? Does it make much more sense now? Okay, great. So now what does it mean? All of it that I have said, what does it mean? It means that if I have to know that how many binary trees are possible whose root is equals to 20, for that I need to know how many binary trees are possible whose root is a factor of 20 and is smaller than 20. I wanted to know the value of the number of possibilities for 4, the number of possibilities for 5, the number of possibilities for 2, the number of possibilities for 10. So how does this scenario look like? This scenario looks like that answer to a bigger problem depends upon the answer to smaller sub-problems. And this is straight off which kind of algorithm? Which kind of algorithm exhibits this trait? Recursion. Recursion exhibits this trait. But here we are not just going to do brute force recursion, because we can just store this value, that number of possibilities for 4 is 2. We can store this value, number of possibilities for 5 is 1. We can store these values and then use them again and again. So this is going to be something very close to dynamic programming, if you have ever learnt about it. So if we know the answer to the smaller values, we can very easily find out the answer to the larger value. Now that will only happen if I first sort my array, isn't it? So the first requirement is that whatever array has been given to you, you sort it, because you do not want to land into a scenario where you have a 20 here, but this 10 is lying to the right side and you do not know how many possibilities are there for 10. So you want this array to be sorted for sure, correct? Does this point make sense to everyone? Now one more thing, when you look at this question told you that everything is going to be unique, because everything is going to be unique, so you don't have to worry a lot, because let's say if there were multiple occurrences of 10, then you might have been confused. Then you might have been confused as in that, hey, for this 10 there are 3 possibilities, and for the other 10 also there are 3 possibilities. So should my answer be 3 into 3? No, not at all. Not because in that case you might end up doing some repetitions also. You might have to take care of those repetition scenarios. So it rids you of all those scenarios by saying that, hey, there are all unique integers only, so you don't have to even worry about that. Okay, so now what does it mean? It means that we need to store the number of possibilities for all the smaller values, and that will help us figure out the number of possibilities for a larger value. That's the only important thing which is there in this question. Now the next thing in this question is, when you go ahead and solve it, where will you be storing these values? If you look at this question, it says that the elements in the array will be lying in between 2 to 10 raised to power 9. So where will you store them? Yes, you can store them inside a map, right? Do not use a memoization array. Those of you who would be using, who would have solved some standard DP questions, what do people do in standard DP questions? This is what we do, right? We declare this of some size, right? But here the values that you have are 10 power 9. Now you cannot have an array of size 10 power 9. I mean, your memory would bloat, you'll get memory limit exceeded, correct? So we can use a map. We can use a map because in map you can have a key of any type. You do not have dependency on the index, right? and then the job would be done. So the first thing that comes to our mind is that we need to sort the array, and after that we need to initialize a map. Now tell me one thing, let's say the name of this map is possibilities, that how many possibilities. Can I say that for the first element, no matter what the first element is, possibility for array of 0 should be equal to 1. It will always be equal to 1 for the first element. Can I say that? The answer is yes, of course, because no matter what this element is, if it is the first element, if there are no smaller elements than that, then there would be only one tree which has this as the root, correct? So I can definitely initialize this map with possibility of array 0 equals to 1, and then I can start processing the remaining elements. When you are processing the remaining elements, how will your algorithm look like? So let's say if you are at 20, what will you want to do? You will want to generate all the factors of 20, isn't it? And do you guys know how to generate all the factors of a number? So you can generate all the factors of a number by iterating from how much to how much. Here you don't have to consider 1 as a factor, so you can start from 2. So you can start from 2 and you can go all the way till factor smaller than or equal to square root of that number n, correct? And now, you know, what you can do is you can just check whether the current factor is actually a factor of n or not. So you can check if n mod fact is equals to 0 or not. If this is the case, then that means you are getting 2 items as factor. The first item is fact itself, and the second item is what? N divided by fact. It's natural, isn't it? Because let's say you have a value 20. Now if 2 is a factor of 20, then 20 by 2, which is 10, will also be a factor. So just by iterating till square root of n times, I will be able to gather all the factors that are there. Now let's say it was for 20 and you gathered that one of the factor is 4 and the other factor is 5. So you'd want to look up inside the map and find the value for 4, find the value for 5, and then do the needful. Do this multiplication, multiply 2 to it further, and so on and on. There is one important edge case, one intelligent edge case. Can somebody figure that out for me? What will that edge case be? Tell me. That edge case will happen for numbers like 36, which are perfect square. Very good. Let's say you have 36. For 36, let's say if at any point of time fact is equals to 6. If fact is equals to 6, the value of first will be 6. And what will be value of second? The value of second will also be 6. In that case, would you want to do a multiplication by 2? The answer is no, not at all, because number of possibilities for 6, because these two values are not different, these two values are same. And because these two values are same, so there is no point of multiplying by 2. See, when these two values were different, then I could confidently say that, hey, the tree which is hanging here is different than all the trees that are hanging over here. But if both of them are same, then by doing multiplication with 2 will just give you duplicates. So we have to be wary of such scenario. We have to handle that. So we have to ensure that if both the first and second values are same, we do not do a multiplication by 2. Is this point making sense? How many of you can gather this idea? Yeah? Okay. So finally what would happen, guys, is that by the time you would have iterated from beginning till the end, for each element you would know that how many binary trees are possible that have that element as the root. So you would know the number of possibilities for array 0, you would know the number of possibilities for array 1, so on and on and on and on. you would know the number of possibilities for the last element, which is array of n minus 1. So what will be your overall answer? Your overall answer will simply be equal to the sum of all the above, isn't it? Because now I know that how many binary trees are possible with a root of 2, how many binary trees are possible with a root of 4, with a root of 5. So if I sum them all up, that will be my overall answer. And of course there will be no duplication in between them. Why? Why? What's the reason behind that? The reason is that all these values are different. Okay? Correct? Okay. Great. So now can you implement this? How many of you can go ahead and implement this? What if we multiply by 2 and subtract by 1? Why do you want to multiply by 2 and subtract only by 1? If you multiply by 2, you would want to divide by 2 also, right? Because all the possibilities that you will get for this and that, you will get the same possibilities by swapping them also. 6, 6. Correct? Okay, great. So I'll show you I have a code pre-written here. Oh, but it doesn't seem to work. Is it so? Is this website unavailable for you too? Okay, interesting. Okay, the final thing that has remained in this question is that you have to know about the rules of modular arithmetic. So what do I mean by that is, because the question says that the answer can be very large, so you have to take answer modulo this value. You have to consistently keep on applying the rules of modular arithmetic, which says that, do you know how many of you do not know the rules of modular arithmetic? Anyone here? It simply says that if you are adding two numbers and if you want to take its modulus with m, then this will be a mod m plus b mod m, and then you have to take a mod with m again on this entire result, whole mod m. This is how modulus is distributed on a and b. The same rule applies for multiplication also. If you're multiplying, the same rule applies. I mean, you have to do a mod m multiplied by b mod m and then whole mod m. This is how you have to go. So if you go ahead and code this approach, code this idea, then in that case, I think, see, everything else is sorted. There is not much problem with implementation. The only thing will be that you have to take care of this modular arithmetic whenever you are doing things like these. Things like multiplications and additions and all. See, addition though you will do eventually. You will take addition of all these things. Now while adding, you have to ensure that you apply the rules of modular arithmetic. And the same thing you have to do while multiplication also. Like while you are multiplying these two, you have to use the rule of modular arithmetic while doing so. Is it up yet? Not yet. Okay, I think that's better. In that case, you guys can sit and probably try implementing this out on your own, and then I'll probably post the code that I have maybe a day after tomorrow or something, after you guys have given some good enough attempt, isn't it? Cool. Can you write it? By the way, I just want to know from you how many of you now feel confident that you'll be able to code this all on your own. I can list down the steps for you. The first step is initialize map. The second step is sort your array. What's the next step? The next step is where you go ahead and iterate on this array. You know, when you initialize the map, we already said that we would say that map of array of 0 will be 1. because if you want to have the first element, the smallest element as the root, then there is only one possibility. And after that I'll iterate from index 1 till the end of the vector. And now here what I'll do is I can always initialize possibilities for, here I am using the word map, so let me do that. I can always initialize map of array I as 1. Why I can always initialize it? Because you know, whenever you pick an element and you talk about how many binary trees are possible, I would say at least one binary tree is always possible, at least one, right? Where we have this particular node itself as the only node. And after this, here we can have that logic where I check for all the factors, f smaller than equal to sqrt of array I f plus plus. Now when we come in here, over here, now we can check if array of I mod f is 0. This is one thing, but one more thing I have to check. I have to check whether this item f is present inside our map or not, because think of it in this manner. Let's say there was no element like 5. If there was no element like 5 in the array, would that element be there inside the map? No. So if f is not there, in that case there is no use of processing things. Okay, so you need to check that as well. So you need to check, I'm just writing the pseudocode, I'm not writing the entire code, and f is present in map. Then in that case you can move on, you can go down, and then you can check what is the number of possibilities that we have for f, what is the number of possibilities f, and n by f as well, because the second factor is n by f. So if both of them are present, you can go down and you can check that how many possibilities we had for f, how many possibilities we had for n by f, and then based on that you can get your job done, right? When I say get your job done, what I basically mean, you can multiply the values that you have. So you can multiply possibilities 4 with possibilities 5, and then if both of them are different, you have to further multiply a 2 as well to it, and that's how you have to go ahead. Oh great, looks like it is back, so you can have a look at what I have written. So see, the first variable I have declared is modulo variable, just to take modulus. The second thing is unordered map. Then I have sorted the array. This I have already told. This also I have explained. I am just iterating from index 1 onwards till the end. Now I have initialized this to 1, and then I am iterating on the factors. Now this is something which I just explained to you. So first I check whether this number is a factor or not, and then I check whether this factor is present inside our map or not, and then array I by factor, which is the second factor, is also present or not. So if this condition evaluates to true, then only I go inside, and when I go inside, what I do, this long expression, this long scary expression that you can see is just because of modular arithmetic drama. That's it, nothing else. So if you remove that modular arithmetic part, all that I am doing, I am multiplying number of ways for first factor with number of ways for second factor, which is array I by factor. And I had to do this typecasting to eliminate the integer overflow issue, because integer overflows can also happen when you are multiplying the values. Okay, now I am checking if factor and second factor are not equal. In that case I am multiplying a 2 also, correct? And then I am adding that value to the number of ways that I have. So basically by the time this particular loop will be over, we will have how many ways are there that are possible for array of I, that are possible with having array of I as the root of the binary tree. And finally we are just summing them up as stated, and then we are returning the answer. Does it make sense? Does this code correlate with whatever idea we have discussed so far? How many of you could correlate? Yeah, okay, so I think the next thing is you head back and try writing the code on your own. And who will tell me the time complexity? What is the time complexity? Let's have time complexity discussion as a homework. So you guys think of the time complexity. Don't be in a rush. Think of the time. See, there are so many things that are happening. Let me tell you. You're sorting also. And then there is a loop inside which there is another loop which is running for square root of something times. N square might not be right. I want you to give a thought to it again. Okay? Because the outer loop is running for n times, but the inner loop is not running for n times. So this is something that you need to look at. So give some proper thoughts and then comment below the YouTube video whatever you think is the right time complexity. We can discuss it there. Okay, cool. So that will be it for today. It was a good question. Discuss it with your friends if you feel like, because the more you discuss, the more you learn. Okay, and bring your friends to these discussions also if you feel they might benefit out of it. Yeah, share it with them, and let's meet again tomorrow. Yeah, okay then. So bye everyone, have a good night.